Hi, in this video, let's talk about changes of state or phase changes. Now the states we're talking about are physical states. They are solids, liquids, and gases. And I'm sure you're familiar with melting ice into a liquid and boiling liquid water into a gas. But it's true for all materials pretty much. You can take like, I don't know, lead, solid lead at room temperature, you can melt it at high temperatures, and in fact you keep on heating it, you can boil it into a gas. That sounds weird, gaseous lead, but it's true. So most materials you can do this. For some other materials they might start to burn and do a chemical change, but in general you have your solids, liquids, and gases. And if you want to change a gas back into a liquid, well then you need to cool it off and condense it or liquefy it. And of course, if you take a liquid, you want to make it a solid, you freeze it. Okay, so there's some terms in here: melting and freezing, boiling and condensing. Boiling, there's a couple other terms you should be familiar with: vaporizing and evaporating. And I guess to complete the whole thing, you can take a solid and directly change it into a gas in some systems by subliming it. Okay, so what's going on here? Well, in the future chapter, we'll talk about the molecules and the atoms that make up materials. Right now, let's just think of them as small particles. So let's talk about water. And a solid form of water is ice or snow. And in that case, we think about tiny little particles of water all sticking together. And they're very cold. The temperature is very low. And remember, we talked about temperature being a measure of the average kinetic energy of molecules or particles. Well, keep that same idea in mind. These particles don't have a lot of motion, not a lot of kinetic energy, so the temperature's low. And if you start warming them up, the molecules move faster. They vibrate in place a little harder, a little faster, until finally they can kind of unstick from their neighbors and get into the liquid phase. Now the molecules, those little particles, have more motion. They're freer, but they still kind of stick together, and they flow about as a liquid. If you keep on heating it, you keep giving these little particles more and more energy, so they move faster and faster, start bumping around, colliding, to the point at which they can collide with all their neighbors and bounce apart and separate into individual particles, and that constitutes a gas. So to understand phase changes, it's really all about two basic principles. First idea is that as you heat things up, that is, go to higher temperatures, that gives those little particles higher or greater kinetic energy, which translates to more motion. And then another characteristic is that all materials have this, this property in which they attract each other. And when we talk more about chemistry, we'll get into the factors that are involved here. They depend on something called intermolecular forces, but essentially molecules are kind of sticky. They like to stick together. Some molecules stick better than others. But those are the two main concepts. These molecules tend to stick, and when they're moving slowly enough, they stay fast, tightly bound together because they're all stuck together. But as you warm them up, it gives them more motion, and they can unstick from their neighbors and start flowing about as a liquid, but still kind of sticky. So there's still these droplets, these liquids, kind of sticking together, clinging together. And you have to give them more and more energy until they bounce around, and they can just actually bounce up into the gas phase or bounce and unstick from each neighbor and become a gas. The process of going from a liquid to a gas can be called evaporation, and it turns out that it's a cooling process. Take that liquid and heat it up till they separate into a gas. Well, yes, it takes heat energy to move the liquid to the gas phase. So where does that heat come from? Well, for this guy, the little sweat droplets of water on his skin, the heat comes from him. He's hot. He heats up the little sweat droplets on his skin, and as the little water droplets of sweat on his skin take up that extra energy, they can use that energy to jump up into the gas phase, to unstick from the neighbors and become gas. And in fact, they carry away that heat energy. And so the person, this man in this case, cools down. We can go a little bit further and talk about the little droplets of water. The little droplets have little tiny particles, and they're all going at different speeds. They have different amounts of kinetic energy, and the temperature is the average of all those little particles, the average kinetic energy. And, right, all the little molecules, the little particles are all sticky, and so it's going to be the particles that can move the fastest that'll have the greatest chances of unsticking from their neighbors and being able to jump into the gas phase and kind of flow away. Okay, and if that's true, those particles with the greatest kinetic energy, if they're the ones leaving, then the little particles that are left on the skin will then decrease in energy, right? The ones that have the most kinetic energy are leaving, which means the ones left behind have less kinetic energy. And you take an average of all those, that's a measure of temperature. If the average goes down, the average kinetic energy goes down, the temperature's going down. So, in effect, evaporation is a cooling process. Okay, let's go the other extreme. Keep on heating up these water molecules, not so that they just simply evaporate, like maybe this puddle in the sunlight will eventually evaporate. The sidewalk will dry up, but let's heat it up more quickly. Put it on a stove. Put some flame on it. Let's get this cooking. And as you heat up the water hotter and hotter, something happens. You get little bubbles forming. What's inside the bubble? Is that air? No, that's water vapor. So as you heat up the bottom of this glass pot, the bottom surface gets really, really hot. And what does that mean? Well, temperature is a measure of kinetic energy. The glass is actually vibrating very, very quickly, the little particles of glass. It's all vibrating very quickly and transferring that heat energy to the water inside, and bumping them around, making them move faster and faster, giving them more kinetic energy, which is raising their temperature. And they get to the point where the little water molecules that can contact the glass are going to move so fast, they can collide with their nearby neighbors and push them around and push them out of the way and form a little gas bubble, where inside is steam, water vapor, water molecules that have unstuck from all their neighbors and have entered the gas phase. Okay, in order to do that, in order to push all the neighbors around, they actually have to push against this external pressure. And not only the weight of the water is pushing down, but more importantly, the atmosphere is pushing down. And so technically, the boiling point, when you start seeing these little bubbles, happens when you can heat up the water to the point which it evaporates so fast that the new gas that's being created has a pressure that equals the external pressure. And so when this new gas has enough pressure, it can push everything out of the way and form a little gas bubble. In this case, it's made of steam. And then what happens? Well, this little pocket of fast-moving water molecules is less dense than the surrounding liquid, right? There's fewer molecules in there. There's less mass, weighs less, becomes less dense. And what we learn about buoyant force? Well, things that are less dense will float. So those little bubbles will float up to the surface. And then when they pop, that lets out the steam. Okay, let's talk about melting. So here this guy's throwing salt on the sidewalk that has a lot of snow and ice. And the idea is he's saving himself a lot of work from scraping up and breaking up that ice. He's going to let the salt melt it for him. So what's going on here? Well, let's think about the process of melting. That's where the little water molecules are tightly held together. They don't have much motion, so they're held fast in place as a solid. You warm them up, they can unstick, move away from their neighbors. They have enough kinetic energy to bounce, vibrate around, to unstick, and now they can flow about. Well, throwing salt on ice, what that does is the little salt particles can stick to the water molecules. And it turns out that water sticking the water is much stickier. It's a much more effective, attractive force than water sticking the salt. And so the water molecules have an easier time unsticking from salt particles than they do from water particles. That means they don't need as much energy to unstick and form a liquid. Okay, so at freezing temperatures, like, minus 5 degrees Celsius, or 32 degrees Fahrenheit is when water freezes ice, so drop that down, I don't know, 28 degrees below freezing, you can still throw ice on the ground. And the water molecules don't have to warm up to 32 or up to 0 in order to melt, because they can unstick from the neighbors because the salt can become their neighbors. That's what's happening over here. This is a salt crystal just thrown on some snow, and as the salt contacts the snow, the snow is made of frozen water molecules, they start unsticking and start melting. And then the salt actually dissolves in that new liquid water and moves out and dissolves more snow. And so you can see how it's melting away from the salt as the salt's helping the snow to melt. And it's doing it at a lower temperature. Antifreeze in your car works the same way. There's another molecule that makes up antifreeze, mixes in with the water inside your car, and that mixture has a harder time of freezing in place. The molecules don't stick tightly together, and so you have to decrease their speed, lower their temperature much farther, much lower, before they can stay fast in place. And so if you use pure water in your car and you left it out in this environment, the water inside your car, the radiator, would freeze and crack the engine essentially. But if you put this other liquid, antifreeze, appropriate name, stop it from freezing, you mix it in there, and now the water antifreeze mixture freezes at much lower temperatures. Okay, last idea. So what are clouds made of? Well, here's some clouds. You got some clouds drifting high in the sky here, over the desert over here, and then this is interesting. Here's a mountain slope. You got some chairlifts for a ski resort, and down below there's a cloud. So what's going on? What are these clouds made out of? Well, they're made out of water, right? So I guess I should rephrase the question. Which phase, which state of matter are these water molecules in? Are they solids, liquids, or gases? Well, it turns out we can rule out one of them if we understand gases a little bit better. Okay, let's think about gases a little bit more in detail. In a gas, the water molecules are moving so fast that even though they touch and collide with other water molecules, they don't stick. They're moving too fast. So even though they're sticky, they have these attractive forces that are trying to pull them together, they're moving too quickly. So they stay as individual particles. Well, these little particles, the smallest pieces of water, these little molecules, they're just too small to see. You can't see gases unless they have some type of color, but you can't see the individual particles of gas. You can convince yourself of this if you like by if you have some glasses, if you wear eyeglasses like I do, or if you just take a cold mirror in the early morning after you shower or whatever, you breathe on it, you can fog it up. And if you watch yourself do this in a mirror, as you kind of breathe on some glass that's cold and you see the glass fog up, look in the mirror and see if you can see the water come out of your mouth and onto the glass. And no, you can't, because water coming out of your mouth is water vapor. It's a gas. So like steam. And once it contacts the cold glass, well then those little tiny particles of water that are in the gas phase, they strike the cold glass and they slow down. They cool off, right? Temperature's a measure of their kinetic energy, how fast they're moving. So when they contact the cold glass, they slow down and they start sticking together. And so as you breathe on cold glass, all the water molecules slow down. They start sticking to the glass and to each other, and they form tiny little droplets, kind of like a fog. And those little tiny droplets are liquid water droplets. So that's the key to understanding what clouds are made of. We have to understand that gases have particles that move so fast, so much kinetic energy, they don't stick together when they collide. And these little tiny particles are too small to see, right? So breathe on a piece of glass. You can't see the little water vapors, the little molecules that make up water vapor. Okay, so if we can't see individual gases, then the clouds are not made of gas. They're not made of water vapor. They're not made of steam. No, instead, they have to be liquid or solid, right? So that sounds a little weird. but here's the idea. You know, I got this little spritzer over here, spritzing the water, and this tiny little water droplets coming out. Well, if you consider the smallest little particles of water all clinging together, forming tiny little droplets, they can kind of float on the air, kind of get carried along by the air. And I know the bigger, heavier water droplets are going to fall by gravity. The lighter ones, they're going to be drawn down by gravity, but the air can kind of pick them up and carry them a while. This boy is over here playing in the dirt, so little dirt particles. You can see it's creating a little fog, if you will. That's solid material, right? Solid dust and dirt. And sure, they have mass, but they're kind of held up in the air. They're kind of floating about. And in the same way, the clouds contain tiny little droplets of water, or if it's cold, the little tiny droplets of water freeze into ice or snow, and they're suspended up there in the sky. Here's something else to consider. This last picture down here, this is a fog. If you drive down this slope, walk down this slope and into this cloud, you wouldn't think of it as a cloud, you would actually think of it as fog. And if you ever walked in fog, you know that you can get pretty wet in there as the little tiny droplets of water droplets that make up the fog kind of stick to your skin, stick to your clothes, and they start beating up and make lots of water droplets. Here's another way to understand how clouds come about. Let's ask a different question. Where's the steam? Where is the gas? Where is the water vapor? So here's some hot teapots. Let's look at these other pictures. Kind of zoom in on it. Okay, where's the steam? Well, you know, they hot kettles. Maybe there's a flame underneath that's warming them up. That's supposed to be a flame. Warming up the bottom of the kettle. The liquid water inside the kettle turning the gas inside here, and then it comes out. So the steam is right in here, where you don't see anything. So what's this stuff? Kind of looks like a cloud. Well, as the hot steam comes out, these little water molecules have so much energy, they collide with the other water molecules coming out. They don't stick together. But now as they come out, they mix with the cool air. And as the water molecules cool off, they slow down. And now as they slow down, they start sticking together. And they form tiny little droplets of water. And they keep going up. Why are they going up? The cool air warms up, the water cools off, and they try and reach, you know, some temperature in between. And it's the warm air in here that now is less dense than the surrounding air, which is cooler, because it's expanded, because it's hotter. It's less dense and it starts floating up. Hot air rises. And this hot air rising carries along the little tiny droplets of water. And we got a cloud here, and that's what's happening outside. You see a bunch of clouds up high in the sky. The water vapor has come off the ground, or off a lake, wherever, gone up into the sky, and carried up there by warmer air. And then as it gets up higher and higher, they start cooling off, they start sticking together, and forming tiny little droplets of water that we really can't see unless you put your hand in there and feel how wet it is. These tiny little droplets are big enough to scatter light so we can see them. So there you go. You know what clouds are made of now. Liquid water or solid water. Okay, thanks for watching.